Good morning, everyone. Myself, P. Vanita, working as assistant professor in the Department of Electrical and Electronics Engineering. In this session, we will continue our study of generators used in renewable energy systems. We will focus on synchronous generators and permanent magnet synchronous generator used in wind energy conversion systems. We will understand their construction, working principles, advantages, and their integration with the power grid. A synchronous generator is an electromechanical device that converts mechanical energy into electrical energy while operating at a speed synchronized with the grid frequency. The generator consists of two main parts, the rotor and the stator. The rotor rotates and produces the magnetic field while the stator remains stationary and contains the armature windings where electricity is generated. The magnetic field can be produced either by permanent magnets or by electromagnets supplied with DC excitation. As the rotor rotates, its magnetic field cuts the stator conductors, including three-phase AC voltage according to Faraday's law of electromagnetic induction. The rotor of a synchronous generator receives DC excitation through slip rings and carbon brushes. The brushes maintain electrical contact with the rotating rotor winding. Unlike DC generators, synchronous generators do not require a commutator. This simplifies construction and reduces maintenance requirements. The operation is very similar to the alternator used in automobiles where mechanical rotation produces AC electrical power. The permanent magnet synchronous generators, commonly called PMSG, uses powerful permanent magnets mounted on the rotor to create the magnetic field. These magnets are usually made up of rare earth materials such as neodymium iron, boron, or NdFeB. Since the magnetic field is produced by permanent magnets, external DC excitation is not required. Permanent magnets can be mounted on the rotor surface, embedded inside the rotor, or placed in special slots. The air gap between stator and rotor is kept very small, often less than 1 millimeter, to improve magnetic coupling and increase efficiency. Because excitation losses are eliminated, PMSCs offer high efficiency, compact size, and reduced maintenance. In direct drive wind turbines, permanent magnet synchronous generators are widely preferred. These generators can have a large number of poles, sometimes more than 60 poles, allowing efficient operation at low rotational speeds. Since no external excitation system is needed, the overall system becomes simpler, more reliable, and more efficient. Another disadvantages is that generator achieves maximum efficiency only at a specific wind speed because rotor flux remains constant. This slide explains the variable speed operation of wind turbines. The generator does not have to remain fixed by varying the rotational speed according to wind conditions. Maximum power can be extracted from the wind. The three-phase AC output from the generator is supplied to a rectifier. The rectifier converts AC to DC. The rectifier converts AC to DC. However, the output of the rectifier is not pure DC. It contains fluctuations called ripple components. These fluctuations must be removed before further processing. After rectification, the output voltage becomes pulsating DC, although batteries can be charged using pulsating DC. Most electronic equipment requires smooth and stable DC voltage. Therefore, smoothing circuits are used. The circuits contains inductors and capacitors that reduce AC ripple and produce nearly constant AC voltage. This stable DC supply improves system efficiency and power quality. Before connecting a synchronous generator to the power grid, synchronization must be achieved. Four conditions must be satisfied. Generator voltage must equal to grid voltage. Generator frequency must equal to grid frequency. Phase sequence must match. Phase angle difference must be nearly zero. If synchronization is not achieved, severe electrical and mechanical stresses can occur. Therefore, generators must rotate exactly at synchronous speed before connection. An inverter converts direct current into alternating current. After rectification and filtering, the stable DC voltage is supplied to the inverter. The inverter generates AC voltage with the exact frequency and voltage required by the utility grid. Modern grid connected inverters continuously monitor to grid to the grid and automatically synchronize with it. This ensures smooth power transfer from the renewable energy system to the electrical grid. Thank you for your attention. In this presentation, we will discuss synchronous generators, permanent synchronous generators, their construction, operation, advantages, rectification process, smoothing circuit, synchronization requirements, and inverter-based grid integration in renewable energy systems. I thank you.